This is my talk. And the nice thing about going right after Sanjeeva is he's given most of my talk, so I can get us back on schedule. Firstly, let me thank Yulu and his team for putting together this symposium, and also for giving me the privilege of speaking at this symposium in honor of Professor Sean Phelps Williams. Your name is not crossed out there. That just happens to be the template that I used. I can't quite recall what Yulu suggested was going to be the title for my talk, but it definitely had CAA in it. So I'm just going to talk about some simulations of jet noise, somewhat similar to what Sanjeeva just talked about, but also talk about the effect of nozzle geometry on the predictions. And this work, as you can see, has been supported by an organization called CERDA, and it's part of a program to develop community noise models for military aircraft. So this is my outline. I'll come back to the comparative study in a moment. The technical part of the talk, which is going to be fairly brief, will give some background, a little bit of problem formulation, the numerical approach, and primarily talk about the results. I want to focus on round and nearly square jets, comparisons for both flow and noise. And then I also want to talk about predictions for beveled nozzles, which were shown yesterday by Vishy, and some comparisons there. And then I also want to address this issue with the effect of initial excitation. Obviously quite a bit to cover, so I'm not going to go into a great deal of detail. Let me go back to the first topic. I think we're getting a little too technical with our presentation, so I thought I'd add something a little bit different at the beginning. When you have known of and admired the work of someone like Sean for so long, it's sometimes a humbling experience to maybe compare your own career or what you've done with his achievements. So I put together what I call a comparative study. Okay, so this is the early years, and we're going to have, this is a table, and we have a number of columns. Here's the column for Sean. This is getting, I think, the Sir Frank Whittle Medal from the Royal Academy of Engineering, I believe. So he's looking very pleased in that picture. I don't have that medal, so I don't have an equivalent. So this is me. This is me when I had a little bit more hair than I have today. So let's look at the early years. We were both born. Sean was born in Wales, and I happened to be born in Wales as well, but my family had been evacuated to North Wales in the Second World War, so it was more happenstance than heritage. Undergraduate degree, University of Southampton, University of Southampton. This is looking really good. So, PhD, Southampton, PhD, Southampton. Now, whilst as an undergraduate, Sean was far more active in useful things than I was making sure that the landlords were kept certain that their rent was going to be paid through consumption of beer, perhaps too much. But Sean was actually the president of the student union, and he also has a lasting achievement, which will only be recognized by people that went to Southampton. This is an earlier picture of Sean. This is the toast rack, which is owned by the Engineering Society. And I think in 1958, Sean went to Llandudno in North Wales and negotiated the purchase of this early bus that used to run around Llandudno. That's an early picture of the bus at the top. And this is a more recent picture. You can see that the Engineering Society has lovingly maintained, the picture you can see. It runs perfectly well. It goes in the London to Brighton rallies and other events. So this is certainly a physical, lasting achievement from Southampton. Okay, mathematics. We'll talk about mathematics now. Mathematical ability. I think anyone that has read Sean's papers, once you get past the excellent introduction in all cases, realize that Sean is an excellent mathematician. Now, my copy of his paper on turbulence convected at high speeds has a packet of papers behind it. It's about 3/4 of an inch thick, and I think that's just going from equation 2.3 to equation 2.4. there's no question that he is a mathematician. My only claim is that my headmaster said when he was writing my letter for university is that Morris can't do maths. Headmasters know what they're talking about. I was once trying to explain to Sean my ideas about turbulence modeling and instability waves. I know he's already mentioned the concept of instability waves and what's it got to do with turbulence. And so he said things like, but I like to work on well-posed problems. I remember you saying that. Unfortunately, I'm not even sure what a well-posed problem is. Okay. Now, as you know, some of you know, he's gone on to a new type of career, this is animal husbandry. Now, all my information about Kobe beef comes from the internet. You notice that raising these cattle is extremely difficult because you have to feed them beer and you have to give them daily massage. Now, I would like to see Sean give a daily massage to that beast. Now, some of you that are vegetarians may not understand the benefits of good beef, but this is a proven fact. Forward. This is a proven fact. If you take an 8-year-old child and you feed him or her half a pound of beef every day for 1,104 days, they will live to be 100 years old. Okay, so I looked at my own, what I would call animal activities, and you can take that any way you like. The best I can come up with is that I like to look after stray dogs. So after that, I might ask the question, do we have anything in common? And I think that one thing is, I think we both learned one of the secrets to having what I think is a successful academic career. I wish I had the secret to having a successful entrepreneurial career as well, but I haven't achieved that. And the answer is, this is a quote from Sean, is you get very good research students to tackle important but interesting problems. And of course, one of the delights of being at university is seeing your own students really go on and do interesting problems and doing them extremely well. So now I'm going to talk about something that one of my current students is doing, which is the technical part of the talk. I'll come back to the number at the bottom left-hand corner in a moment. So, as we know, there are various methods for noise prediction. Some of them are based upon doing RANS calculations. Okay, which way? Thank you. Okay, some are based upon RANS predictions coupled with some form of acoustic analogy. They're reasonably fast. It really depends. It doesn't actually provide a direct connection between the flow and the noise. You have to do modeling of the statistical properties of the turbulence, and we still are working on this problem after 40 or 50 years, in fact. Or you can do DNS or LES, as Sanjeeva just so expertly explained. This does provide the direct connection between the unsteady flow and the noise, but it's rather like running an enormous experiment. You have incredible amounts of data, and you're not necessarily sure, of course, unless you're very smart, as to what you actually want to do with that information. And generally speaking, these have been run for simple geometries and generally don't include the nozzle in the jet calculation. So I'm working on a hybrid methodology along with a number of other people around the world that are also doing this, which is a hybrid RANS-LES. So you use RANS where RANS is good, you use LES where LES is good. I'm using the detached eddy simulation methodology, which uses unsteady RANS, which is effectively steady RANS in this particular problem, say for the nozzle flow, which transitions then to a large eddy simulation. For the separated flow, a number of other people, particularly the Russian group with Schur and Strelitz, working with Phillip from Boeing, are really doing some excellent work in this area. Very impressive work given the lack of computer resources that they have available. General formulation. Of course, the equations are averaged in some fashion, use eddy viscosity, model for the unresolved stresses. I'm working with a polar grid and generalized coordinates, but just for grid stretching, and then I use Sanjeeva's and Konstantinescu's method for taking care of some of the problems with the azimuthal discretization, but you don't want to know the details. The Spalato-Morris turbulence model is the one I'm actually using. It describes the evolution of the eddy viscosity, and it was actually developed for external aerodynamics. And it is in no way based upon any equation of motion whatsoever. It's a purely empirical methodology that says that the transport of any quantity should have a production term, a destruction term, and a diffusion term. And these terms were constructed in order to get excellent agreement for external aerodynamic flows. But it turns out, oh, by the way, it's gone up to 2, because those are 2 equations. Jack Siner says he loves to come to my talks because I show 2 or 3 equations on every slide. So I'm going to point out this time, we're going to keep a count. Oh, we're up to 4. Of course, you'll recognize that this is upside down and backwards, but the idea behind detached eddy simulation is that there's a length scale in the typical RAMS model, and it's based upon distance from the wall. Once the distance from the wall gets to be, in fact, larger than the local grid size, the method naturally transitions, if you use the grid size of the length scale, into a large eddy simulation. In fact, if you neglect transport effects in the Spalato-Morris turbulence model, you can show directly that the eddy viscosity now looks just like the Smagorinsky model. So it's a very effective way of using a RANS-based method to transition naturally to an LES type of method. Okay, it's all done in parallel. I used careful boundary conditions, which are really essential. Do a lot of things in the wall, in the nozzle region, in order to try and minimize the effort expended in getting that flow correct. And then I put in a random excitation, which I'm going to come back to in a moment, which is rather crude compared to what Sanjeeva described. It basically decides whether to turn on or off at a given time step the excitation, purely on a binary decision. Extrapolation of a sound to the far field. Here we use the famous Phelps-Williams-Hawkins equation in its permeable surface implementation. And actually, if you go back to Sean's paper, there's the quote that says, "It is also assumed," and this is quite reasonable because the application I think in mind was moving surfaces, generating noise, that in all practical situations, the surface S is impermeable. But what is remarkable about that analysis is it also admits and includes the permeable surface version, and that's what has been so powerful and has been so useful in CAA applications, to get the information from the near field out to the far field. So we're using Faraset's formulation 1A, which is a solution to the Phelps-Williams-Hawkings equation, and in fact the numerical implementation is really the work of Ken Brentner, my colleague at Penn State and one of Sean's former PhD students, in his code called PSU WOP-WOP, which is a rotorcraft noise prediction code, although it's essentially a Phelps-Williams-Hawkings code. Don't include the quadrupole terms. I really worry about this one. We use an open surface both at the inflow and the exit, so it's not a closed volume, because I'm not exactly sure how to deal with putting the surface through an active turbulent flow region. There are some issues there. These grids are of the same order. This is for circular and square nozzles, typically at the order of 1 million grid points. Okay, these are the grids for the square nozzle. You see, it's not square, it's sort of smoothed in the corners. And this is the outer grid, this is the inner grid. Okay, let's just look at some results. This is a comparison, just concentrate on the circular one, comparison between measurements and predictions for the centerline decay of the velocity. This is a high Mach number unheated jet. Centerline turbulence intensities really predicted quite well from the Florida State measurements, I guess. Radial distribution, so the flow characteristics are really being captured quite well by a moderate grid size compared to DES. So far as the noise radiation is concerned, we put this Phelps-Williams-Hawking surface at 6 diameters. At the sample time, well, the sample time is 0.05 non-dimensional units. That would tell us, in fact, that we might be able to go up to 154 kilohertz for this model case. But of course, the resolution spatially, as Sanjeeva mentioned, just doesn't give us the ability to do that. So I estimated about 1.6 for the, and Sanjeeva said 1.5. So we're about agreeing there. These are the predictions for the circular jet. Forget the dash line. Notice I'm not being very fair to myself because I'm using a quite expanded scale here. So in fact, the difference between the predictions and the measurements is within 2 dB, and different measurements are within 2 dB of each other. If you look at the spectra, in fact, these are spectra at different angles relative to the downstream axis, and shown here is some of Vishy's data in terms of a narrowband spectrum, and we're sort of getting into the right ballpark with these calculations. Okay. Bevel nozzles. Vishy showed these yesterday. A very nice concept. Obviously has a lot of development work before it can go into practical application, but it's a nice idea. If you really can't reduce the total power by more than a small amount, why not send the sound somewhere where it isn't particularly harmful? And so this is one of the ideas behind the beveled nozzle. It sort of looks like an ellipse from the end view, and 0 degrees here is on the longer or scarfed end of the nozzle, and 180 is what will probably be the noisy direction. One thing you're able to predict, this is the highest bevel case, and the scale is clearly expanded, is that in fact the thrust axis, which I take as being the line following the point of maximum velocity, certainly deflects upward. I get an angle which is slightly greater than the measurements in terms of the deflection angle. But in terms of the mean flow development, doesn't seem to be much difference between, say, a circular case and the mean flow development along the center line for the beveled case. And this is along the geometric center line. It doesn't account for the slight thrust axis. I wouldn't believe these values down to here because you need to average for a very long time to get statistical stationarity in these downstream locations. But if you look at the noise, there's quite a change. This is for an unheated case, and the changes are more significant for heated cases, as Vishy showed yesterday. These are the predictions for the third octave spectra at 0 degrees, which is the scarfed or the quiet direction, and 180 degrees, which is the noisy. All these bumps are just a function of the fact that third octave spectra, you have to join points together. So if I didn't show the points, it wouldn't look quite as spiky. These are the measurements, once again, third octave values, and you can see all of the characteristics, levels are really well predicted, and the crossover in terms of some being quieter at low frequencies, noisier at high frequencies for this unheated case are quite well captured. And if you just put everything on a rather messy chart, you can see, particularly in the noisy direction, the third octave spectra is captured quite well. We're not doing quite as well in the quiet direction, but still, for the purposes of demonstrating a concept or looking at optimization, for example, this is certainly, I think, quite helpful. Initial excitation. This is something that when you don't have the nozzle, you've got to somehow put in some excitation. In fact, you could argue perhaps if you do have the nozzle, if the flow coming out is smooth and quasi-laminar, like an average calculation, you're still going to put something in order to trigger the proper evolution of the turbulent shear layer. But one has to worry that if you put, say, small disturbances in the vicinity of now a sharp edge or a boundary, a nozzle, you might be generating something which is completely non-physical, just totally associated with scattering from your excitation. So the obvious thing to do is to turn the excitation off. So that's what we did. We did a calculation where we ran the circular jet with excitation, got the whole thing going, and then turned the excitation off. And it didn't change. It got the same results without excitation once we'd started. In fact, you could probably start it with an impulse, I think, and get it going, and then once it was going, it would be self-generating. But I don't think that would work if you didn't have the nozzle in there. And the reason I think that is to do with the fact that when you put a nozzle in, you get a self-excitation phenomena occurring. I talked about this multi-block idea with an outer grid and an inner grid. The way that we have it set up is, in fact, they don't exactly overlap. So one grid follows the inside of the nozzle, one grid follows the outside of the nozzle, and they're separated by one grid point. So there is a finite thickness to the nozzle lip, and what happens is that you get a little absolute instability, a little wake instability just downstream of the nozzle, which keeps on generating unsteadiness, which keeps the turbulence going. I think if you had zero thickness for the lip, or no lip at all, that eventually disturbances would die away and you'd go back to just laminar, smooth mixing. Okay, so a short technical presentation there. We've done calculations with the nozzle included. I'd say we're getting pretty good agreement with experiment. The more grid and computer resources you throw at anything, the better the agreement can be. I think this certainly shows the principle. We're heading towards doing calculations for different geometries. Some of these are running at the moment, but they just weren't finished by the time the meeting started. Particularly looking at the heated bevel nozzle, which seems to be a very attractive case because you get noise reductions at all frequencies in the quiet plane in that case. Williams-Hawkins, or as I read this, I looked up Sean on the web, and there was this Harvard newsletter, and apparently the president there, or the chancellor, said that this should be pronounced Fox. Is what he said pronounced Fox. So Fox Williams, Hawkins. What's the effect of closing the service? I think that's actually a really important problem, and it needs a lot more work. And then we need to address when do we need to excite and when we don't excite. The more natural can be the excitation, the better it ought to be, because it removes a certain degree of arbitrariness from the calculations. So that's all I have. Thank you. Okay, I'd be happy to entertain one question, if it's an easy one. Yes.
Let me ask you this. I think with like rectangular nozzles, particularly those that are closer to square,
yeah,
the initial conditions or the boundary layer that is developed from internally in the nozzle determines a lot of the downstream characteristics.
Yep.
So in your modeling, is that always going to be a very difficult issue unless you...
What we will be able to capture are secondary vortices in the corners, those kind of effects, and I think that certainly is going to have an effect on the evolution. For the rounded case that I showed there, we just didn't get any significant secondary flows, so the square nozzle looked like the second nozzle. So we're running a much sharper corner rectangular case. Strictly speaking, the easier way of doing that is to go to a rectangular Cartesian-based grid, but my code happens to be polar, so you can't win every case. Okay, thank you.